Good morning, or whatever time it is when you're watching this video, and welcome to the Section 3.2 lecture video for Statistics at Morton College. As always, I'm your professor, Dr. Scott Spaniel, here for another lecture video. So today we're going to be talking about what are measures of dispersion. So in the previous video, we looked at how to figure out where the middle of your data was. And so that's one way to talk about data is where is the middle. Another way to talk about is how spread out from that middle is it, or how spread out is it in general. So that's what we're going to be looking at today is different ways to measure how spread out your data is. So you can go ahead and take out your note sheets, which as always can either be found in Blackboard or in my math lab, depending on your course structure, and turn to page 11 to follow along. So I'm going to define this idea of dispersion, and then we're going to look at the simplest measure of it, and then we're going to build up another measure of it. So dispersion means the degree to which the data is spread out. So that's all that word means. How spread out is your data? So one way to measure that is called the range, which we denote with a capital R. The range of a variable is the difference between the largest value and the smallest value. Okay, so all we care about is how far apart all the data is, from smallest to largest. That's all this tells us. And so it's really easy to calculate. You just take the largest value minus the smallest value. Okay? So let's do that. Let's do an example of that. So the Insurance Institute of Highway Safety crashed the 2007 Audi A4 four times at 5 miles per hour. The cost to repair for each of the four crashes was $976, $2,038, $918, and $1,899. Compute the range, and then we want to talk about what does the range not tell us about this data set. So to compute the range, we find the largest value and the smallest value. So our range is going to be 2,038 minus 918, which is $1,120. And just like with measures of central tendency, our range has the same unit of measure as the data values themselves. Now, this tells us how far it is from the largest data value to the smallest data value, but it doesn't tell us how spread out the data is in between. It could be that all of our data is either down here near the smallest value or up here near the largest value, or it could be fairly evenly spread out. And that's what the next thing we're going to talk about helps us do. So deviation is another way to talk about this idea of dispersion. So deviation is based on difference from the mean. So how far are you from the middle of your data? For a population, for the ith observation, it's x sub I minus mu, and for a sample, it's x sub I minus x bar is how we find deviation. Okay, so that's how far does a individual data value deviate from the mean. So what we want to do is compute the deviations from the mean of each data value in the above sample. What would happen if you took the sum of the deviations about the mean for every observation? Okay, so that's what we want to try here, is I want to try out this idea of finding deviations. So in order to find deviations, the first thing we have to do is find the mean. Okay, so let's take x bar is going to be 976 plus 2,038 plus 918 plus 1,899 divided by 4. All right, that's what we talked about in the last lecture video. So 976 plus 2,038 plus 918 plus 1899 is 5,831 divided by 4 is $1,457.75. Okay, so now what we want to do is we want to find the deviation for each one of those data values from this mean. Okay, so to do that, we can list the data values. So here are my x sub i's: 976, 2,038, 918, and 1,899. And then what we want to do is we want to find x sub I minus x bar. So we're going to take each one of these x sub i's minus our mean. So we take 976 minus 1457.75, and we get negative 481.75. And then we take 2,038 minus 1457.75, and I get $580.25. Notice, for each one of these, I'm taking the x sub I minus the mean. So if your data value is less than the mean, you get a negative deviation. If it's more than that, you get a positive deviation. So then we get negative 539.75. And we get 441.25. Okay? So if we look at those like that, and you might think, well, now that we've found each of the deviations, if we find the average of those deviations, then we'll end up with the mean. Unfortunately, that's not how that works out. Okay? Because if we add all these together, so negative 481.75 plus 580.25 plus negative 539.75 plus 441.25, we get 0, which should make a little bit of sense because remember, the mean is the balancing point of the data. So if the data balances, the deviations from that should add up to 0 to make that balance, because if they didn't add up to 0, then the scale would lean one way or the other. So the question becomes, how can we deal with this issue? How can we figure out an average for these deviations if we can't just add them together and then divide by 4 because we'd always get 0? Well, one way to do that is to make these all positive. And one way to make these all positive is to square them all. Okay, so we could square all the x sub I minus x bars. Okay, so let's do that. So negative 481.75 squared is 232,083. Sorry, I wrote 82. 83.0625. 580.25 squared is 336,690.0625. Negative 539.75 squared is negative 291, not negative, sorry, positive, because remember when you square a negative you get a positive because negative times a negative is positive, so 291,330.0625, and then 441.25 squared is 194,701.5625. Okay, and now if we add all those up and then divide by 4, we'll get an average of the deviations, which is a fairly, might be a good way to do this. Okay, so if I add these up, I get 1,054,804.75. Now, and then if we divide that by 4, right, because there are 4 deviations, so divide that by 4, I'll get an average of their squares. Now, there's a problem here, right? Which we haven't talked about yet. Which so far what I've done is I've averaged these values, and I've got a square of the units. So how can we now get rid of that square? Well, we just take the square root of that answer, right? Because the opposite of squaring something is its square root, and we get 513.52, and I'm going to round to the hundredth place because this is in dollars. And so there is an average of the deviations, which is something we're going to call a standard deviation. And this is the basic process of how you would do that by hand. You're finding the average of those deviations, but one of the problems is you get positive and negatives, so you have to square them, and now we get a number that finds us that average. So that's the general idea of what we're going to do. It's not exactly what we're going to end up doing in the end, but it's very close, and that's why it works the way it does, why these formulas you're about to see on the next screen work the way they do. So let's go and flip over to the next page, and let's write out the formal definitions here. So this idea of squaring it gives us a new type of statistic called the variation. So the variation of a variable is the sum of the squared deviations about the population mean divided by the number, except I should have put the word population here. So the population variation of a variable is the sum of the squared deviations about the population mean divided by the number of observations in the population n. That is, it is the mean of the squared deviations about the population mean. The population variance is symbolically represented as sigma squared. So this is a lowercase sigma, and it's denoted with a squared because it's the square of the deviations. And its formula is the sum, basically what we do is we find the deviations like we did on the previous page minus the mean, and we add those all together, squared. And then we divide, this should have been a capital N. By capital N. Okay? And in shorthand, that formula is the sum of all the x sub I minus mu's squared over capital N. Remember, this capital sigma just means the sum of, to add them all together. So we're just going to skip this part. Okay, and we can do the same thing for a sample variance. Okay, so before I actually do that, let me go back a page. So this value right here that we found before we took the square root is the variation. Okay, before we took the square root for using this population formula. Now, we can do the same thing, but for a sample, and we're going to call that lowercase s. Remember, for population, we use Greek letters, and for samples, we use Roman letters, which are just the letters you guys are used to using every day. So we compute the sample variance by determining the sum of the squared deviations about the sample mean, and then dividing the result by n minus 1. Okay, we'll talk about why n minus 1 here in a second. But it's the same formula, except with an n minus 1. So it would be the sum of x sub I minus x bar squared over lowercase n minus 1. Okay, so that's the formula. And I'm going to skip this computational formula again because we don't really need it. Because for the most part, we're not going to use these formulas. We're going to use technology to find these. As you may have noticed when we were doing this example together, this took a while. And we only had 4 data values. So what are you going to do if you have 200 data values? You're not going to do this all by hand. So we'll look at here in a minute how to do this using technology. Now notice that the sample variance is obtained by dividing by n minus 1. If we divide by n, as you might expect, right, like we did for the population, the sample variance would consistently underestimate the population variance. So in general, we find that in general, when you use n, you are dividing by too large of a number and you consistently get a variance that's too small. Later in this class, we're going to use these standard deviations to help us guess at what the population value is given a sample value. And so when we're guessing, we'd rather guess wider, bigger than too small, right? Because if I'm trying to guess your age range, I'm more likely to get it right with a bigger range. So I don't want to underestimate things. So whenever a statistic consistently overestimates or underestimates a parameter is called biased. So to obtain an unbiased estimate for the population variance, we use n-1, because by subtracting 1 from n, we're dividing by a smaller number. When you divide by a smaller number, you get a larger result. We call n-1 degrees of freedom because the first n-1 observations have the freedom to be whatever value they wish, but the nth value has no freedom because the sum of the deviations must be 0, so the nth observation must be whatever value makes the sum 0. So basically the idea behind that is these first 3 observations could be whatever they wanted to be. But then this last one had to be, based on what those 3 were, the last one had to be 1899 so that this ended up being 0. So these first 3 were free, but once you know the first 3, the last one has to be fixed to make the deviation 0, is the idea. You don't really need to know that. What you need to know is that when you use the formula, you divide by n-1, and that's called degrees of freedom. Now, as we saw in our example, if we simply do this without taking the square root, we don't actually end up with a value that's useful to us. So what we're really going to look for is not just the variances, we're going to look for the standard deviations, what are going to be called standard deviations. So for the population, we just use the symbol sigma, and it's obtained by taking the square root of the population variance, right? Because the square root cancels out the squared. So the written out formula for the standard deviation would be the square root of the sum of all the x sub I plus mu's squared over capital N. And the standard deviation, I should have used the word population here. The sample standard deviation is S is obtained by taking the square root of the sample variance. So that would be the square root of S squared, or the square root of the sum of all the x sub i's minus x bars squared over n-1. And I noticed the typo I wrote here, which is that should be a minus, not a plus in the first formula there. Okay, so that's the idea of how these formulas work. And like I said, for the most part, we're just going to use technology. But one really important thing to take away from here is if you want to find the variance given the standard deviation, you just square the standard deviation. If you want to find the standard deviation given the variance, you take the square root of the variance. Okay, so that's the idea. So now let's look at some examples, and specifically, let's look at how to use technology to do some examples. So this first one says, the following data represent the travel time in minutes to school for 9 students enrolled in Sullivan's college algebra course. Treat the 9 students as a population. So compute the population standard deviation. Okay, so let's look at how to do that using our Google Sheets and ClassCalc. Now I'm going to show you how to do this with Google Sheets, but in general, I would use ClassCalc. So to do this with Google Sheets, it's going to work basically the same way that all the other ones that we've done so far have worked. You're going to put in a formula. So I'm going to put equals, and then I'm going to start typing standard deviation. And notice I'm going to get a lot of choices. The one I want here is I want to treat this as a population. So I want to use STDEVP. Okay? And so then I select my population, which is in B, and then I hit enter. And there's my population standard deviation. Now notice, because the formulas are different, if I try to do the sample standard deviation, and let's see which standard deviation this is. Yeah, the regular one, if you don't write anything else, you'll get the sample standard deviation. It just assumes this is sample data, which makes sense in most cases. Or you can add an S. I think. Did I do that wrong? Or you can add a .s and you get exactly the same result. But the key is if you just use the regular standard deviation, that gives you the sample standard deviation. If you use standard deviation with a p at the end, you get the population standard deviation. And that was pretty straightforward. And then if we wanted to do a sample of these students, we could select a sample, and the process would work out exactly the same way. So this is the population standard deviation, right? And this was for the sample. Okay, so you get different answers. Now, we can do the same thing with ClassCalc. So let's go ahead and just use the next problem to talk about ClassCalc, shall we? And how to do those in there. Okay, so suppose that you are in the market to purchase a car. With gas prices on the rise, you have narrowed it down to 2 choices and will let gas mileage be the deciding factor. You decide to conduct a little experiment in which you put 10 gallons of gas in the car and drive it on a closed track until it runs out of gas. You conduct this experiment 15 times on each car and record the number of miles. Describe the data set. That is, determine the shape, center, and spread. Which car should you buy and why? So shape is it skewed or not? Center is measure of central tendency, so that's either median or mean. And then spread is how spread out is it. So that's measures of dispersion. Okay? So what we can do is if I go to 3.2 problem 2, and remember you can find these data sets, links to these data sets in Blackboard, and if you want to try these on your own, you want to copy this by going to File and then make a copy. And then that way you'll be able to edit it. You should not be able to edit this one because I don't want us to accidentally screw up the data here. So if I try and copy this, let's see what happens into ClassCalc. So you hit Command-C or Control-C to copy it, and then you can hit Command-Paste to paste it into here. And notice it figured out that car 1 was not an actual data set. So I'm going to name this C sub 1, but you could just call it A. And then I'm going to try, because I don't really know how this is going to work, I'm going to try and paste this stuff. Actually, if I just select these numbers instead of choosing the whole row, I'm going to try and paste these into here. And let's see if that works. Nope. It did not like that. What it did instead, though, is it put it down here into a separate table, which is fun. So let's call that C sub 2. And the way I'm doing the subscripts is by using the underscore key, which is the shift and then the key to the right of the plus symbol. I mean the left of your plus equals on your keyboard. But like I said, you could easily just use A and B. Okay? And so now what I want to do is I want to So now what we want to do is we want to find all the things we just talked about. Now, if you remember back to the last video, you could go in and do these individually. So if I go to Stat, and then I could just choose standard deviation, and I can tell it to find it for C sub 1, and there's both of them. It gives me the sigma and the S. So if it's a population, it would be this number. If it's a sample, it would be this number on the right. Or we can do all of this at once by going, instead of just going to Stat Basic, I can go to Stat Advanced and choose 1 var stats. And now I can type in C sub 1, and it'll find all of the different data values I really want for this car. So we've got the mean X bar is 223.47, and then we can see the median is down here is 223. And then we can get the standard deviation, and this is a sample, so I'm going to use S, but sigma is also right here. So S is 21.797. Okay, and so that's all the information we're going to need in order to find the shape, the center, and the spread for car 1. And then I can do the same thing for car 2. So I go to Stat, Advanced, 1 variable statistics, and I type in C sub 2. And you could easily use, instead of using these C's, just use A and B, right? So for car 2, we get X bar is 237.2. The median is down here, right, where it says X and then sub med. So 230. and then S is 49.060. Okay. So now I wrote all this down in my notes. So if we look at these, what shape, first of all, is this first distribution? Well, the mean and the median are basically the same number. So that means this is symmetric. Okay. And so that means we're going to use the mean for our center. And then our dispersion is 21.797. And then for the second car, notice the mean and the median are not equal. The mean is greater than the median. So that means this is skewed to the right. This is skewed larger, which is to the right. And we can tell that because whichever side the mean is of the median is the way it's skewed, right? Because the mean is not resistant, so it gets pulled away from the center more easily than the median. So this got pulled to the right, so that means that it's skewed right. And so that means we're going to use the median as our center, and then here's our standard deviation. Okay. So now you want to choose which car to pick. So we could pick car 2 based on the fact that its center is larger than the other one, or you could choose car 1 based on the fact that it's more consistent because its spread is smaller, right? Something is more consistent if it's less spread out. So there's an argument to be made for either of these cars depending on which one is more important to you. For example, if you have a long commute or you drive long distance a lot of time, it may be more important to you that you know how much mileage you're going to get on a relative drive versus if you just want to make sure over the long haul that you end up getting the best gas mileage, you probably want to pick car 2. Okay, so there's an argument to be made for both. Okay, so at this point, what I'd like you to do is pause the video, and you can try using either ClassCalc or Google Sheets to try these other two problems here. And then we'll talk about them here in a second once you've tried them. Okay, so now that you've all had a chance to try these two problems, let's try them, go through them together. So the first problem asks us to find the population mean and the range for the number of smallmouth bass caught per day for each fisherman. Okay, so we can do the mean for each of these. So if I do Ethan and Drew. So Ethan, I'm going to use Google Sheets for this first problem. So the mean average of A, and then I want to do the average of B. Oh, and they have exactly the same average. Okay, so that's one thing to notice here. And now let's do the range of both. So to do the range, I just do the for both of these I got 10. I just do the largest value minus the smallest value. So let's just do those by hand. So the range for Ethan's largest value is 24 and his smallest value is 5. So 24 minus 5 equals a range of 19. And for Drew, his smallest value is 1 and his largest value is 20. So 20 minus 1 is also 19. So based on just those two numbers, Ethan and Drew basically had exactly the same 10-day fishing trip. They basically caught exactly the same fish. But if you look at the data values, you might say, well, that doesn't seem quite right. So let's try finding the standard deviation to see if that tells us anything more. Okay, so I'll just use Google Sheets again to do this one. So standard deviation P, because they wanted the population standard deviation. And I want to do that for column A. And then for Drew, I do the same thing. Standard deviation P on B. Okay, and we get 7, 9. So what we can find what we found by looking at those data is that Ethan was much more consistent. So he had a lot less spread than Drew. So he had a much more consistent fishing trip because he had the smaller spread. And so this is a good example of the limitations of range. Because range only tells us how big is the total spread. It doesn't tell us how spread out things are inside of that. In this case, what happened is Ethan was in the high single digits almost every day, except for one really big day and one small day, whereas Drew was all over the map. There was no consistency on what happened each day. Okay. And so now let's try this last one together as well. So I'm going to go to my data set in Google Sheets. This is the fourth problem. So we'll just copy this stuff over to, let's do this one in ClassCalc. So I'll just copy these over to ClassCalc. I'm going to change this first one, column header, to be L for Liberty. And this one I will put to N for no till. And now it just wants to know, it asks which plot type do you think is superior? So what we want is we want to get as much data about these as we can to be able to answer that question. So I'm going to go ahead and use one var stats for this. So to get a bunch of stats, so one var stats for L. And then I'll just go ahead and before I look at that, I'll just go ahead and do the same thing for N. So one var stats for N. And so what we can see is I'll write this stuff out in the notes and then we'll talk about it. So we've got X bar is 35.9. And then this one had a median of 36 and a standard deviation of 4. Notice it said sample, so that's why I'm using S, 4.26. And then for no-till, we get a mean of 35.9, a median of 35, and a standard deviation of 4.86. Okay, so it's really close which one is superior, but I would probably say that the Liberty is superior because while the means are exactly the same, it has a slightly higher median and it is less dispersed, so it's more consistent than the other one. Okay, so that's the idea. So that's how we can use these two options of technology to help us find standard deviations for data, which is how most likely I'm going to ask you to find these in general. So now that we've talked about this, let's talk about some uses of standard deviation. And the first of these uses is called the empirical rule. So the empirical rule says that if you have a distribution that is roughly bell-shaped, so that means it roughly looks like a bell. It roughly looks like this. Let me just go and go back to full screen. Then the following things are true. Approximately 68% of the data will lie within one standard deviation of the mean. That is 68% of the data is between mu minus sigma, 1 sigma, and mu plus 1 sigma. They fall between those two numbers. Approximately 95% of all the data values will lie within two standard deviations of the mean. That is 95% of the data is between mu minus 2 times sigma and mu plus 2 times sigma. So between those two data values. And then last but not least, approximately 99.7% of the data lie within 3 standard deviations of the mean. So that is 99.7% of the data lie between mu minus 3 sigma and mu plus 3 sigma. And so here's a graphical representation of that. So if you split it up into pieces, how much would be in each of these pieces? So you can either use this picture or you can use the data at the top to tell you how many to answer these questions. So one thing you might want to start with when you do a problem like this is take this graph and fill it in with the mean and standard deviation. So for example, in this case, the mean is 515 and the standard deviation is 114. So that means 515 would go here on my picture. And then I would add 114 to get this number right here. So 515 plus 114 is 629. And then I could add 114 again. So that would be 743. And then I could add 114 again, and that would be 850, not 857, and then we can also subtract 114. So 515 minus 114 is 401. Subtract 114 again, and you get 287, and then I can subtract it again, and I get 173. Okay? And so now you know what all the numbers in the problem are referring to. So like, for example, what percentage of SAT scores are between 401 and 629? So we can see here's 401, here's 629. So between those would be all of this, and that's 68% of the data. What percentage of SAT scores are less than 401 or greater than 629? So we're starting in the same spot again, but now we want to be less than that, so that's over here, or greater than that, so that's out here. So that's everything outside of the part we just found. Well, how much is their total? Well, there's 100% total. So if I'm doing everything except this, that'd be 100 minus 68%, which would be 34%. Okay, and that's the idea. So what percentage of scores are greater than 743? Okay, so we do the same idea. Let me just erase some of the stuff I don't need anymore. Okay. So then for the last one, we're looking at this number here, 743, and we want to be greater than that. So one option is, if you're using this nice picture here, is you can just add up these two numbers. So it should be 2.35% plus 0.15%. So if you're using this nice picture here, which you could easily use every time and just erase or print off multiples of them, it's got all those little numbers in it. So that would be 2.5%. Or you can use this idea up here of these bigger numbers, the big grouping. So if I'm looking at 743, that means I want to get rid of all the stuff in the middle, but that's in this part, right? Which would be 95%. So that's 100% minus 95%, which is 5%. And then I can notice, well, it gets split in two. I'm stuck with this part over here and this part over here. So those are equal, but in two pieces, so I divide by 2, and that's 2.5%. So those are two different ways to find this value, but like I said, you can always just use this chart with all the individual values written out. Okay. So at this point, if you wanted to pause the video, you could try these. So we've got a bell-shaped, so now that you've had a chance to try these, let's go through these together. So I've got my bell-shaped graph, and I could write out the standard deviations. So I'm starting with 100 in the middle, and I'm adding 15, which is 115, adding 15 again, that's 130, adding 15 again, that's 145, and then subtracting 15 is 85, subtracting 15 is 70, and subtracting 15 is 55. And so if we want to say what percentage of people have an IQ score between 70 and 130, well, that's the middle. That's two standard deviations, right? This is minus 2 sigma. This is plus 2 sigma. So that would be 95%. And then how much is outside of that? Well, that's 100% minus 95%. So that would be 5%. And then if we wanted to do greater than 130, well, greater than 130 would be half of this last problem. So that would be 2.5%. Okay, so that's that one. Okay, so here's another example, same idea. So we could start once again by drawing a bell graph. So this one starts at 4 inches, and then we add 0.007. So 4.007, and then 4.014, and then 4.027. And then we subtract it. So 3.993, 3.986, and 3.979 would be our values. So about 68% of bolts manufactured will be between what lengths? Well, that's within one standard deviation. So that's between one standard deviation below and one standard deviation above. So that's 3.993 and 4.007, right? Because 68% is plus or minus 1 sigma. So what percentage of bolts are between 3.986 and 4.014 inches? Well, we find those are 2 standard deviations, right? This is minus 2 sigma and plus 2 sigma. So that would be 95%. And then there's a typo here. So company, get rid of this part. I just copied it. I got copied down. What percentage of bolts manufacturer will be between 4.007 and 4.021? And this would be a good example of where the easiest thing to do is just go to the chart and add, right? So we're 1 sigma and 3 sigmas, so we just add 13.5 and 2.35. And so that's 15.85%. Okay? And so that's the idea with the empirical rule. Now, the key to the empirical rule is that they have to be roughly bell-shaped. But most distributions, or not all distributions, are going to be roughly bell-shaped. So that's where one more rule comes into play. It's called Chebyshev's inequality. So for any data set, regardless of the shape of the distribution, at least 1 minus 1 over k squared times 100% of the observations will lie within k standard deviations of the mean, where k is any number greater than 1. That is, at least 1 minus 1 over k squared times 100% of the data will lie between 1 minus k sigma and 1 plus k sigma. Now, this is not bell-shaped, so this is basically saying this is the minimum number that will work. So what minimum percentage of gasoline stations had prices within 3 standard deviations of the mean? Well, to do that, our k is this 3, so we just do 1 minus 1 over k squared times 100%. So that, in this case, our k is 3. Okay, and so we can put that in a calculator. When we do that, we get 88.9%. Now notice, the empirical rule says approximately 99.7% of all data should fall within 3 standard deviations of mean when it's roughly bell-shaped. So if we don't know the shape of the distribution, we have to be less accurate. We can't assume as much data falls within 3 standard deviations of the mean. So what minimum percentage of gasoline stations had prices within 2.5 standard deviations of the mean? So same idea. So 1 minus 1 over 2.5 squared times 100%. So we can put that in our calculator. And that's 84%. So what are the gasoline prices that are within 2.5 standard deviations of the mean? Well, within 2.5 standard deviations of the mean means either minus that or plus that. So it's going to be 1, not 1, sorry. It's going to be the mean, which is in this case $3.06, and the standard deviation is 0.06. So 3.06 minus 2.5 times 0.06, and 3.06 plus 2.5 times 0.06. So we're taking 3, the mean minus the number of standard deviations times the standard deviation. And for this one, I get 2.91. Then we do the same thing, but we add it. We get 3.21. So 84% of gas stations had at a minimum, 84% of gas stations had a price that was between $2.91 and $3.21 per gallon. Okay? And then what is the minimum percentage of gasoline stations that have prices between $2.94 and $3.18? Well, to figure that out, we need to know how many standard deviations is that from the mean. So to figure that out, we just take the data value, 3.18, minus the mean, and divide by the standard deviation. So the data value minus the mean divided by the number of standard deviations. And in both cases, we get 2. And so now we can use Chebyshev's inequality to figure out the minimum percentage. So that would be 1 minus 1 over 2 squared times 100%, which is 75%. Okay, so that's the idea of how to use Chebyshev's inequality. So if you want to try these last ones, you can, or you can practice on the homework. I think this video is probably long enough as it is, so we're going to go ahead and stop there. This problem is very similar to the one we just did. So with that said, make sure you're doing all your homework and quizzes. And if you have any questions, feel free to email me or contact me through Remind. And also make sure if you're in a class with a class meeting, make sure you're coming to class to ask questions. Or if you're in a class without class meetings, make sure you're doing the discussion posts.